Well, hello everyone, and welcome on the session DEV308. My name is Alexey Ivanchenko. I'm solution architect here in AWS, and with me, Vadim Kazulkin. He is head of development in IPL Labs, and as well, AWS Serverless Hero. And for me, as the solution architect, main goal is to help my customer for scaling their business and help them modernize their workload without them spending too much time and effort on these processes. So today we are going to talk about how to build modern application with the help of Aurora DSQL. For that, we are going to dive deep into building blocks of this database and its architecture. We will go through few code samples because this is 300 level session, and we will go through the performance and challenges that you can see within the DSQL, and of course we will do the wrap up on what we have learned today. And with that, I'm passing the word to Vadim. Vadim?
So the question is why we need another serverless database. We have already several offerings on AWS. The list is not complete. You see Amazon DynamoDB, RDS, Aurora Provisioned, and Amazon Aurora Serverless v2. I would like to talk about these databases, but especially in terms how they fit for the serverless workflows. And I'm working a lot with AWS Lambda, so just how these databases can be approached and talked to from AWS Lambda. So let's start with DynamoDB. It's really the ideal fit for serverless workloads. You don't have any infrastructure management here. It's the database, it scales up and down for you. And if it scales down, it scales up without any cold start of the database, so it's not noticeable for you. You have single millisecond digit performance. So that's really cool database. Also, in terms of other things, so I really prefer it, but there are also challenges around that. So everything is a trade-off. So for example, it's no SQL database. And with that, there's another mindset comparing to relational databases, how you design those tables, how you involve the schema afterwards. Yeah? It's not very easy. And there are also challenges around certain things, like by default, DynamoDB is eventually consistent. You can turn various things to be strong consistent and pay more for it, but for example, there are restrictions, global secondary indices cannot be strong consistent, for example. And there are also limitations in terms of transaction, how many items can be put in one transaction. So there are certain limitations with that. Now moving to other databases, they are all relational databases and we love them. I personally come to working 10 more years with Postgres, and I like these joins and many tables and all that stuff, and it has its benefits. But especially in terms of how RDS fits into serverless approach, there are certain limitations. For example, there is a lot of infrastructure work to do. For example, you need to define VPC, security groups, and you need to define the size and the family of the instance, and so on. And also with that, you cannot scale compute and storage with this database. So you have the certain size, and then you need to increase the size. You can have multi-AZ, just that you don't have kind of the outage by increasing one side, and then the next side will be increased automatically. And there are also challenges around connection management if you talk from RDS database from Lambda. If the number of connection to the database is a factor of the database of the family size. And if you have a lot of Lambda function, and they scale simultaneously, you can run out of connections talking to RDS database. There are solutions how to mitigate that. For example, RDS proxy by providing something in between, like for multiplexing. But of course, it's another component. It's managed one, but it also has cost associated with that. It can be even latency and so on. So there are other challenges with RDS. Now moving to Amazon Aurora, provisioned one. It's mainly the same advantages and disadvantages as with RDS. The only one exception, you can scale the storage independently of compute with that database. Now moving to Amazon Aurora Serverless V2, we are kind of approaching this world where the relational database are more suitable for the serverless world. Here you can scale compute and storage automatically. You don't need VPC. You might have VPC if you would like to have private traffic, but you are not required to do that. You also not define the instance sizes. This is more Aurora capacity units, and you can say, I would like to scale between this SCU and that SCU. You can scale to 0 this database, which is not possible for RDS and Aurora provisioned. And it's sometimes very important because on your testing and testing environments, you would like to, if you don't use it, you don't want to pay it. So that's why, especially for RDS and Aurora, you provision the smaller instances for those test and staging environments. For Amazon Aurora Serverless V2, you can specify scaling down to 0, but then you have the disadvantages. It might take up to 15 seconds, to scale up, in case you specify to scale down to 0. By default, it scales to 0.5 ECUs. And also, if you scale down to 0, you will lose the cache right near the instance. And that, by scaling up, the performance of the first queries might be slower because, the cache needs to build up. So you see here different challenges, and Aurora Serverless V2, you can use RDS proxy with that, but they also offer data API. So you can talk to the Aurora Serverless V2 like you talk to DynamoDB via HTTP. This is this kind of solution in parallel to RDS proxy. You can decide you can use still RDS proxy or data API. But data API is complete separate API, so you need to rewrite your code in case you would like to adjust. And RDS proxy you can simply use you need only to change the endpoint. So the question that is kind of being asked is, can we have AWS database offering which is as serverless as DynamoDB in terms of not having to deal with the infrastructure at all, scale up and down very quickly without cold starts of the database, but provides the benefits of the relational databases like these ACID things. And with that, I will pass the word to Alexei.
Thank you. Yeah, so for that, to address these questions, we have introduced Aurora DSQL last reInvent, and we made it generally available in the middle of this year. So what is the DSQL? DSQL is the serverless database, which means that you don't need to have any infrastructure to manage. You don't need to bring your database down for patching or updating. You handled by us. It's providing 5 nines of availability, and you get scaling compute and storage separately. You scale the reads and writes separately, which provides you virtually endless scale. And through all this scale, with all this scale, you get strongly consistency all the time. So when you would like to look for the DSQL, first of all, you would like to look for DSQL if you are searching for a database that supports ACID transactions through multi-region. You want to feed the database for your serverless architecture or microservice design, or you have the application that is following event-driven approach, or you don't know how spiky will be your traffic tomorrow or day after tomorrow. And of course, if you want to continue utilize already existing tooling and continue to work with SQL. And now, this all sounds pretty interesting, but how exactly we achieving all this? For that, let's dive into the design of the DSQL. And we will start with single region cluster. Single region cluster is active multi-writer cluster distributed across multiple availability zones. The data is replicated across 3 zones. You have one endpoint for reads and writes It supports simultaneously and concurrently, and you don't have any instances to provision. You can send just requests to the database, and everything else is handled by it underneath. With the no instances to provision, you don't have anything to stop for patching or updating. We also do it by ourselves. And with the single region setup, you're getting 4/9 of availability. In the same time, with the but behind the scene, behind the single endpoint, you have the not just one or multiple Postgre instances that are hidden and running. No, there is, instead of that, what's really powered this SQL is the distributed disaggregated architecture. We took critical components of monolithic OLTP database and separated them into separate services. We separated them into the connection management. We separated into the query processing, isolation enforcement, transaction journaling, and storage. Each of these components works independently and are tuned for its specific role. Each of these components is working with the fleet of the compute resources that can scale independently and can adjust to the workloads. You get one endpoint for both reads and writes, so that means that your reads and writes are always local, and the only thing which is traveling across AZ is transaction commit. And also, as I said, you're getting 4/9 of availability with the single endpoint. In the same time, with multi-regional cluster, you are getting 5/9 of availability and multi-regional consistent writes. It provides 2 regional endpoints. Both of these endpoints support concurrency reads and writes, and together it represented as the single logical database. There is also the third region there, called witness region. Witness region participates in the write quorum and works as the tiebreaker to decide which region can continue to write in case of the network partitioning. The witness region receives the data from the regional cluster. It also holds limited amount of the encrypted transaction log, but it doesn't have any cluster or any endpoints. So if we will look on the high-level architecture or building blocks of DSQL, you will find their front end, you will find query processor, adjudicator, journal, crossbar, and the storage. Query processor does most of the SQL processing job. It acts as the dedicated Postgre engine for each transaction. And there can be as many query processors as there are concurrent connections to the database. Adjudicator determines whether the transaction can be committed while following the isolation rules. Each shard key in database is owned exactly by the one adjudicator at any given moment of time. Journal makes all the transactions durable and replicates the data between availability zones and regions. Each transaction always assigned to the single journal. Crossbar merge the data streams and direct them into the storage nodes. Storage nodes provide access to your data. Storage nodes holds the replicas, multiple replicas, and each storage node contains the specific range of the data based on the database key. It may look a little bit overwhelming or sounds a little bit overwhelming, but let's take a look how does all these components work together. Let's start with the standard read transaction and a basic select statement. Let's imagine that we are the user in the US East US West 1, and we are willing to order food from a local pizzeria service and somewhere here in the Las Vegas. So what's happening there? We deciding that we want to get the restaurants that have the rating 4 or higher. So we're executing the query for select asterisks from restaurants where rating equals or higher than 4.0. So what happens behind the scenes? Your application making the connection to the DSQL frontend. Frontend allocates the query processor and pass your statement to the query processor. Query processor reads the local clock and set the transaction start time tau start. Sorry. Now your read-only transaction begins. The storage is automatically, and what's important, transparent to you, are partitioned according to the database key. That's why query processor consult with the shard map to understand where your data, in which storage node it is located. And because this is read-only transaction, query processor doesn't need to follow the writer path. It doesn't need to go through the adjudicator or journal. It can go straight to the storage to retrieve your data. Storage nodes doesn't return pages, it returns rows. Storage nodes also can process predicated pushdowns, filtering, aggregation of the rows before sending them back to query processor. Together, all this stuff significantly decrease the amount of the data that need to travel across the network and decrease amount of work that need to be done by the query processor. So, and comparing to traditional database, we don't have any monolithic cache sitting aside. So when query processor needs to get the data, it goes to the storage node, which is located in the same region, in the same availability zone where the query processor is located as well. So your reads are always local. So then query processor return then query processor return the results from the storage node. They all merge together and return it to you. So what's happening next? Next, at this point, if you continue to interact with the front end, you're building the interactive transaction. You start the transaction, you do some work with database, you do some work with the client, you maybe go back and forth multiple times, and eventually you commit. How does it look? How does it look, for example, in our case, when you decided to order the pizza? You select the restaurant, you browse the menu, you choose the item, you add the item into your order, you place the order, and basically that's hitting the commit. So what in traditional database, how it will look in traditional database? Most probably you will have to place some logs and do some checks, potentially across the region, for each statement in your transaction. This adds latency to your operation. Query processor acts differently. It acts as the holding tank for all your statements in your transaction. It reads data from the local storage nodes and saves it into the local memory. When it needs to write the data, it's already writing the data into the it changed the data of the local saved data in the memory. And it accumulates all the changes within this local memory and waits for the commit. And then when it needs to commit, it just follow the writing path and sends the data to the adjudicator to check the full transaction, to the adjudicator to check the data. So as you can see, query processors do a lot of heavy lifting. It's basically the heart of the DSQL architecture. And query processor is running in Firecracker, lightweight virtual machines called also micro VMs, and they are running on the bare metal query processor host. And we can run thousands of pre-provisioned micro VMs on the single host. So every time when you connect to the DSQL and start to using it, we are making sure that there is enough micro VMs running to handle your workloads, and we can scale them automatically as it is needed. Each query processor is fully independent and isolated, so they never communicate to each other. And talking about the isolation, in DSQL we are supporting transaction-level isolation called snapshot isolation. Each transaction operates on the consistent snapshot of the database as it was at the beginning and the start of the transaction. Your transaction begins and proceeds through the SQL execution path, where all the reads are happening always with the consistent snapshot. At the storage level, these reads are implemented using the technique called versioning concurrency control, or multi-versioning. The storage engine keeps multiple versions of the same row and allowing access to the older versions of the row while not blocking of creating newer version. And when basically write operation occurs, like insert or update, it's not immediately written to the storage, applied to the storage. Query processor spools all the changes into the local storage, into the local memory, and creates a private workspace for it. Private workspace for this transaction. And this approach basically enables you read your writes capabilities. So for all subsequent reads within the same transaction, you're working with the pending changes. Your read transaction see the pending changes that you already applied through the writes. So when your transaction issues the commit, DSQL needs to understand whether all the changes that were applied within the transaction and spooled locally can be applied to the storage, can be written to the storage. And that's where the adjudicator comes into the play. It sits in the writer path of DSQL and decides will the transaction be committed and written. Its job to detect and resolve the conflicts that are happening between the transactions to ensure the consistent writes. So to do this, the query processor forms the payload, creates the payload to send it to the adjudicator, and this payload contains all the necessary information to make this decision. We have the write set there, which contains all the items modified by transaction. We have the post image set, which contains the copy of the table rows after applying transaction changes. And we also have the start time of the transaction, tau start, which plays the crucial, critical role in deciding which will be transaction committed or aborted. So, and we will talk about this part a little bit later. So when when two transactions comes, what's basically happens? Here we have two transactions, A and B. They started almost at the same moment of time, but transaction A was committed slightly before transaction B. So what happened in this case? In this case, adjudicator will analyze the payload of both of the transaction and examining their writer set and start time. It will look for all the changes that were made after the start time, tau start, and it will look for overlapping or matching rows that was changed. And it sees that both of the transactions are trying to change the same row, and because they cannot both of them change the same row at the same time, because transaction A was committed slightly before, transaction B need to be aborted. At that moment of time, transaction A is allowed to proceed and decide the commit timestamp, tau commit. And if there is two transactions which have different writer sets, or this writer sets contains the not overlapping or not collapsing, not conflicting writes or rows, in this case, both transactions can be committed, can be allowed to proceed, and both transactions will be assigned the tau commit. So once adjudicator decides that your transaction able to proceed, what exactly makes it durable? In traditional database, durability happens on the storage level. Transaction is considered committed only when it's written durably to the storage. The storage layer is then responsible for recovering your committed transaction in case of failure. But these things comes with the price. For that, you need to have the checkpointing, you have to have the logging, you need to carefully coordinate between the memory and the storage synchronization to be able to recover in case of the failure. And all this adds lots of latency and lots of complexity to the system. So DSQL manage this complexity by using the journal. Journal is internal component that was written for the decade and was optimized for ordered replication of the data between multiple AZs and between multiple regions. It scales horizontally, so transaction can come into any of the instances of this journal. Journal coordinate to maintain ordered streams of communication of committed transactions, and then crossbar, which is pulling the changes, pulling the transactions from the journal, routing this transaction to the storage. And using this order to ensure that all the transactions are written to the storage in the proper sequence. So once adjudicator decides that your transaction is committed, it sends the payload and commit timestamp to the journal. Once the journal acknowledge the write, acknowledge your transaction is durable and atomically committed. The journal sends success code back to the query processor, and crossbar at this moment begins to pull the data from the journal and route it to the storage. The query processor at this moment sends success code back to you, to the user, and for you, from this perspective, the transaction is successfully committed. And now I want to draw your attention to two components that are crucial in this all the workflow. Remember that tau start and tau commit. This is the time. This is crucial because you cannot get a strongly consistency without synchronizing on the time. You cannot coordinate them if you don't have the reference clock, which you can trust, and you know that you can trust to this tau start and tau commit. For that, for solving this issue, and achieving this reference clock which we can trust, we have introduced Amazon TimeSync service. With TimeSync service, with dedicated timing hardware that are located across AWS and AWS Nitro system, we having the directed GPS dictated reference clock that are located on the EC2s. In DSQL, it effectively allows us to have globally synchronized clock with the microseconds accuracy time. With all of this, I'm passing the word to Vadim to talk about authentication and authorization, how it's happening. Thank you.
Yeah, so let's look into Aurora DSQL more from a developer's perspective. So the slides are not switching. Okay, something. So.
Yeah,
Okay, now it's working. So thanks. So now let's talk about authentication. How we normally authenticate to the relational database. Okay, it's now not working once again. Okay, now. So normally we use user and password. And with that, it might happen that somebody can get access to this password and misuse it. So normally we need to rotate this password, which we sometimes forget. And this offers the attack vector there. So DSQL doesn't use any password. But what does it use instead? It uses tokens to authenticate. And the tokens are generated by AWS SDK, and it's fast, and what's very important, the local cryptography. And this is more or less the same that is used behind the scenes if we talk to S3 DynamoDB. But these tokens will be generated for us. We don't deal with that. In case of DSQL, we will probably need to deal with that. What's important is they are very short-lived. If somebody intercepts this token, it's probably already expired, which is a good stuff. So now let's look how to generate this token. This is one of the examples we use here, AWS CLI request. We send here AWS DSQL generate the bconnect admin auth token, give the host name and how much time to expire. As short as possible is also okay. What we will get back here is basically the response, and the response is the whole token. And we can use this token to authenticate instead of the password. So for example, you can use that to authenticate using pSQL. Yeah, this is how we talk to the Postgres database. pSQL, we simply export it to the environment variable called pgpassword. And then if we do pSQL quiet connect, then this password will be, this token will be used instead of password. In case you use something like the Beaver or some other tool to authenticate, you simply grab this token and use it instead of password. Yeah, this is how it works. The cool thing is that the DSQL team released their integrated query editor, SQL editor, in the browser several weeks ago. So you can simply go to the DSQL page, and then you can simply do all the SQL stuff in the browser, and this token thing will be done for you, basically, behind the scenes. So you don't need to bother with that. But of course, sometimes you would like to have powerful tools like dbbeaver and use that. What I would like to show you is how easy it's to create Aurora DSQL cluster, especially single region cluster. You see we don't have any scroll bar here, which is surprising. If you already created RDS, then you probably know how many choices do you need to meet. Here's the only thing more or less that you need to do is just more or less give the cluster the name. And everything else is already there. Yeah, there is enabled deletion protection, which is a good stuff. You can remove it. You can customize encryption settings, and you can add the tags. That's basically it. Of course, for the multi-region cluster, it's a bit more complicated because you need another region, just to select another region, then select the witness region, but basically the settings will be the same. So really, really easy. I would like to show you code examples. Please raise your hands who can understand the Java code. Okay, lots of people, which is good because I'm the Java guy and I feel understood myself. So now let's take this subset of application that Alexei showed you, and this will be kind of only the ordering part. So you see API gateway and a bunch of Lambda functions, how to create order, get order by ID, or get orders by created range. Like, give me all the orders from the 1st of November until the 13th of November. And we store that in the Aurora DSQL. I will show you example with AWS SAM, but you can use SDK, you can use CloudFormation or Terraform. Basically, this is very generic example. You can reuse it for all applications, especially if you talk from Lambda to Aurora DSQL. First of all, you need to pass the Aurora DSQL cluster ID variable, environment variable. This is the cluster ID. You create the Aurora cluster, the SQL cluster, and then you can grab the cluster ID. You can provide as a default value or environment variable here. And then you can pass it to create Aurora DSQL cluster endpoint, which is kind of, you can use this variable. It always follows the same pattern here to create this. And I export that as an environment variable for all Lambda functions of my application. And as you see below, this is the Java code. I simply grab it by system get environment variable, and then I use it to create this JDBC URL. JDBC is the protocol for Java to talk to database, to relational database. So the Aurora DSQL cluster endpoint that I passed as an environment variable is a kind of substring of that. And what I need to decide also to give is the authorization stuff. So here I simply allow Lambda function to talk to the Aurora DSQL, and here I need to provide resource IRN in this Aurora cluster, and cluster ID is also kind of used as a variable for that. So pretty generic logic. Now let's look into the example, Java example. So basically it's a good practice to create, to use and instantiate the so-called server-side connection pooling. And it just not only for Java, there are solutions for Python, for all programming languages. The reason that it still makes sense because the creating of the connection is still not free. And the connection might expire and may be kind of fetched once again. So it's still a good practice to use that. And I use for Java Hikari data source pool. And I create that and say how many connections. You can even say one connection in the pool because basically it's a single-threaded or single-process application, and that's why Lambda only needs one connection just at time, and then it does the thing sequentially. So I create this here, and this is the logic to get the connection. Yeah, you see here in both places what we are doing here, we are fetching the token and set it as a password. And there is Aurora DSQL SDK, which does the same what I showed you with AWS CLI. This is basically, you need this to create this generate of token request, provide endpoint, time to leave, and then this token will be generated for you each time, and you need to pass it. What you already see here, we need to fetch this token on two places. First, by creating the connection pooling, and second, each time that we get the connection to talk to the database. And it seems like a boilerplate code. And that's why AWS team improved that. They started with Java, but now also for other languages, they release so-called connectors. And these connectors help you to handle this token generation automatically for you. So you don't need that. And if you looked in the previous slide, that was the only dependency to AWS SDK is to fetch this token. All other code is simple JDBC code. So simply you can reuse that what you already had. For example, if you migrate to the database, there was no dependency to DSQL. And by removing that, we can remove all dependencies to the DSQL. So there is no password management, and now it works since last week also for Python PG and PG2, and also for Node.js. There is Node.js Postgres and Postgres.js driver. So how does it look? We need to add the dependency to this connector there in our dependency management, but now our code doesn't have any dependency to DSQL. It's a pure JDBC, pure Java code, how we talk to the application. You see, we don't have this set get authentic auth token, and we don't have set auth token. But how our application understands that this connector should be used. The whole magic is in this red line. We additionally say it's AWS DSQL in the path, And with that, this connector will be triggered instead of poor JDBC Postgres treiber. So this is kind of the only dependency, is explicit dependency in the string, which says that this connector should do its work, and it will generate fetch the auth token and place it instead of the password for us. So huge improvement of, I would say, readability of the code. So what are other benefits of DSQL? It works really well with familiar object relation mapping frameworks. You probably all use them. You have some entity like order. You can annotate them, the properties like order ID with a column in the database, and simply save the stuff. And it works with all of them. For example, for Java, the Hibernate is a popular one. For Python developers, SQL, Alchemy, or Django. Yeah, and it all works with them. So we don't need to change our code. Let's talk briefly about performance of this database, because Alexei explained the architecture, and it could sound like a magic. So the question is it performant database, or it's all this magic may impact performance? So first of all, my goal was to measure performance from Lambda function. Yeah, so I measured the performance of the Lambda function, which talks to the DSQL, so that the SQL time is kind of there. I used Java as a programming language. I only focused on measuring warm start times. I didn't focus on the cold start time of the runtime. Like Java, it has implications, but it wasn't the goal. That's why I only also focused on 99 percentile, just to exclude the impact of the programming language. And I did the performance measurement for single and multi-region cluster. What was not the goal? That's very important. I didn't want to compare the performance of the databases that we talked about. RDS, DynamoDB, Aurora Provision, Serverless v2, because it deserves the whole talk. And sometimes you cannot compare like DynamoDB with relational databases. And I didn't want to test the performance at scale, just not putting 10,000 transactions per second or just queries per second. And I didn't want to test performance when scaling. I don't have an impact how storage is scaled, query processor, adjudicated. It all happens behind the scenes. So my goal was just to do some basic stuff and see how quick that is. So I showed you this application with ordering. The database structure is very simple. I only have two tables, order and order items. And order has order ID as a primary key. It has created timestamp values, such a thing, and order items has product ID and so on. And I have two indices on the items table, like order ID, because I fetch items by order ID, and also I have one index on the order table on the timestamp, because I fetch the results, like timestamp between one day and another day. So very simple structure. I don't have user table, I don't have product table, only two tables. So the first measurement was I am doing like creation of one order containing two items. So basically, these are three inserts in one transaction. One insert into order and two inserts into order item. If you see the results, let's look into this lila one. It's P90. In 90% of the cases, we have that result that is not kind of worse than that. And you see, it's just for P90, for single region cluster, 20 milliseconds or something around, and for multi-region cluster, 40 milliseconds for three selects. So considering a single region cluster, it's kind of 7 milliseconds per insert, which is, I would say, okay. It's comparable to DynamoDB. For multi-region cluster, it needs to commit in another region, so the performance is kind of twice as slow, which is normal thing, in case you need multi-region. Another measurement was get order by ID, and then get two items. I can do it with one join, no problem. I wanted just to do two joins without joins, like getting the order by ID, and with that ID, and then getting two items with another select. So there are two selects, and you see then P90 lila one, 12 milliseconds for two selects by using primary key. For getting the order, and then the index for getting the order items. You see that the performance is the same for single and multi-region cluster because it's the read operation. And the read operation is always local. It always uses the local endpoints. So the performance of all reads is the same for single and multi-region cluster. So I would say two selects, 12 milliseconds, a good use case. This is a more sophisticated, just get orders by created date range. And I intentionally limited the query that it returns only 100 orders maximal. And then for each order, it gets the items, and I have only 2 items, different items for each row. So basic for each order. So basically, I have 101 selects, 1 select for order, and then for each of 100 orders, I get 2 items. And you see 100 selects, P90, 200 milliseconds for 250 milliseconds for 101 selects. I think it's a compatible, very compatible result. Another thing I wanted to test, because the specification says there is no cold start of the database. And you can measure it. I did that, so my goal was I created a single multi-region cluster and did some operations, and then I didn't touch it for 3 days. And then I did the first select via the console, just not via the Lambda function because it has performance implication. I simply just used pSQL and said select order by ID and some existing order. And I just did it 4 or 5 times, the same, just 3 days, pause, and then select. What you see here, the medium latency in this case was for single region cluster 165 milliseconds, for multi-region cluster 169 milliseconds. So of course there is a small latency because the things needs to be warmed up. If I don't use something, something needs to be persisted, but it's not noticeable. It's not 15 seconds like Aurora Serverless V2. It's just one time for the first select or first operation at 160 milliseconds. So I would say no cold starts of the database. It's simply not there. So now let's talk about, there are also constraints, and you need to understand them, and because that might have certain implications. So let's first start with quotas. Each AWS service has its quotas, and there is even AWS service called service quotas, where you can go there, select the service, and you can see these quotas or constraints. Yeah? In DSQL is no exception. So there are some important ones that I would like to raise the attention. Maximum number of connections. It's by default 10,000. It's a huge number, and you can even adjust it. Yeah, all other databases relational that we talked about don't have that value, and you cannot raise that. So it scales beautifully. Yeah, there is no problem just to have 10,000 Lambda function talking to it in parallel to this database. It's just due to the architecture of querying processor, QP, it just scales beautifully. Maximum transaction time is 5 minutes maximal. Alexei will be talking why those limits are as they are, but you need to think of it as just mostly for the microservice application. So in case you have some analytics job that needs to run more than 5 minutes, probably it's not the best fit, this database. But for certain normal microservice type of things, 5 minutes for transaction seems to be okay. Maximum connection duration is 60 minutes. So 1 hour. In case you design the server-side connection pool, you need and you define the time to leave of the connection. Please define it no longer than 60 minutes, because you will be disconnected. And in case you define lower, the pool will take care of this. And the same if you are talking through the database through pSQL. After 1 hour, you will be disconnected and need another token. Yeah, you need to grab another token, then you are in for 1 hour. Maximum number of rows changed in the transaction. In one transaction is only 3,000 rows. And by changing, I mean delete and update. So in case you have such a use case, like I would like to delete 1 time per year all orders and items older than 5 years because I don't need them from the accounting point of view, you need to think about how to divide the job into parts so that no more than 3,000 rows will be changed. That brings you just to think from the backend perspective how to divide it. Yeah, because normally you would say delete from with timestamp. No, you will get an exception if the number of rows will be more than 3,000. The same for update. Maximum size of modified data in one transaction, 10 megabytes. So you need to think just, if it's normal data, then you probably will not hit that limit. There are also other things that are currently not supported, and I will stress it currently. There are no reason why it's cannot be supported. It might come every day, but until today it's the case. No support for JSON and JSONB. Yeah, so it's not 100%. It's Postgres compatible, but the SQL doesn't support all features. There are no columns with default values. There are no temporary tables. There are no triggers currently. I used them a lot previously, but now it just brings the business logic to the trigger. It's difficult to refactor. But I used, for example, triggers to set the timestamps to now as a default value. It was kind of one of my favorite use cases. I can do it in the backend as well, but anyway. There are no sequences. That's unusual. You can use time-based UUID version 7 instead of this. This is a 36-digit number, and version 7 it supports that you can order by time. And sometimes it's okay. For example, you can design order item IDs like UUID because you don't expose them. That's fine. But for the things like order ID that you would like to expose via email, that somebody can call the call center and say something is wrong with my order, they probably don't want to say 36-digit number. So you need to think how to map in this rare situation to the normal value. Yeah? Maybe they will be supported later. There are no partitions. In case you have multi-tenant application, it might be interesting. Yeah? In case not, probably you don't use it. And you can use only functions written in SQL, which is probably fine. Yeah, you can use probably C++, but it's not supported. But I think SQL is okay. Another things that are not supported, constraints or commands, foreign keys. That's something really unusual, probably. You can do your joins, but there is no foreign key support which will ensure the data integrity. And that might be crucial because I like foreign keys, and I sometimes, or nearly always, I would say, define something on delete cascade there. For example, if I delete the order, I would like that all order items will be deleted automatically. And I can do this with foreign key on delete cascade. It's not supported. Another way to do it is to do it via trigger, which is also not supported. Yeah? So this is then up to you to think and write the business, this in the business logic, that you delete the order and you delete the all order items in the business logic, not relying on foreign key on cascade currently. Yeah? There is no truncate, like we can delete the whole data in the table, and there is no vacuum, but the architecture of DSQL just doesn't require vacuum because of the limitations and constraints that we talked about. There is also no PG vector support in case you would like to use something for embeddings and so on. This database is currently not for this use case. You can use other Postgres compatible databases, RDS, Aurora, or OpenSearch that support that. So this is for normal microservice applications. And with that, we have some final thoughts. Alexei, so once again, these features might come all, yeah? But now you need to think about that.
Yeah. With all of that, let's see what we have learned today on this session. So first thing, which is very important, that thanks to the query processor running into the Firecracker micro VM, we're getting virtually endless scale. We're not only able to scale it to whatever size, we can do it fast. And as we saw from the tests, the cold start is almost nothing. And thanks to the architecture, we can adjust different components of the system very dynamically, depends on the workload, and clean up resources after us very effectively. And as in any serverless service, we currently have some constraints that are needed to get the better performance and get the better results. So here, for example, 5 minutes length of the transaction allows us to get the better write consistency and get the better performance from when the adjudicators need to decide and resolve the conflicts. It also helps us to clean up the resources using the garbage collector, which resulting in the fact that now we don't need vacuum by design because all the reference will be just cleared. And with the 3,000 rows that can be changed within the transaction, we have the stable performance with only one flash of the buffered memory. And to get the best of your usage of DSQL, you should create many connections to your to your front end, parallel concurrent connections, which will result in a lot of query processors, which will basically do the horizontal scaling. You should consider to use small rows and small transactions, so it will decrease the load to the adjudicator for deciding which transactions are in conflict and to resolve this conflict. For the same reason, you may consider to use separate clusters for each of your microservices, again, to have less conflict and to have less aborted transactions. And if you will find any bottlenecks, or you would like to know where the money goes, Explain Analyze will help you with this. And of course, don't forget about client-side connection pooling. This also will help you with your performance. And with that, I'm passing the mic to Vadim to wrap up.
So one benefit of Explain Analyze, you can use Explain Analyze verbose, and it will also display you the price, the DPUs now. And you can do it in this browser editor. We didn't touch about pricing, but it helps you just to understand how much does it cost to run that and that query, by the way. So, okay, I go back. So, yeah, to wrap up, DSQL is very easy to set up and get started. Nearly no infrastructure management, multi-region out of support right from the beginning. ACID support is there completely as we like, especially no eventually consistency at any scale, which is very important. At any scale for single and multi-region cluster, and high availability is also there. Now I will provide you an opinionated comparison of the databases that we talked about, DynamoDB, RDS, Aurora, Aurora Serverless v2, and now DSQL, but only for the serverless workload. Please understand, 3 stars doesn't mean it's 3 times better than 1 star, but 3 stars means it's just a better fit for the serverless workload, or solves the problem better than 2 stars, and 2 stars solves the problem better as 1 star. So setup experience, Aurora DSQL, brilliant, like DynamoDB. Simply is just quick and you are there. Auto-scaling experience, up and down automatic. You don't need to do anything to decide how much to scale and how much to scale down. It's just no cold starts. Beautifully. Exit support completely there, like for all relational databases. No need for connection side pooling. Yeah, you don't need a DS proxy. There is no data API. It scales beautifully. You can have tens of thousands Lambda functions talking to a database, and it works. And yeah, it works with familiar drivers and object relational mapping framework, as we like. But of course, yeah, it looks beautiful, like Aurora DSQL is kind of supports every use case. There are challenges, and you need to be aware of that. The first one, as we talked, the feature gap to be 100% Postgres compatible is currently quite big. Yeah, you need to follow, and especially if you start now from scratch with your application, if you know that you can adopt to this, I think. But if you would like to say, I would like to migrate your application, you will probably run into situations that you need sequences, you need foreign keys. Yeah, you run into this 3,000 updates in one transaction. You need to rewrite code, and it poses the question, is it the right time to migrate? Yeah? But if you start from scratch and you know that you can start, and I'm pretty confident that the features will come with time. And of course, the service quota are a bit restrictive for serverless database users, like 5 minutes transaction time, 3,000 rows. We know these quotas from DynamoDB, and we appreciate them because they are there for a reason, to get the best performance. But for relational database users, more or less would like to do everything with the database with any limitations, which is sometimes also not a good thing, because the query performance will be worse if you will join how you would like. It just also doesn't work like this. And this limitation also are there to just deliver the best experience. But anyway, you need to know them, you need to understand them when you design or migrate. So this is the QR code of my GitHub repository with the examples, yeah, with that, the code that I have shown you with connectors and without connectors, so you can scan, and or you can write to me, you can find me like on LinkedIn, and I will give you the link to the repository if you wish. And for that, thank you very much. Don't forget to rate the sessions.
It's very important for us.
Yeah, to receive the feedback. And we are here to answer your questions. I think it's kind of the silent sessions, but we are here. Thank you very much.